You are welcome to Organic Chemistry Series 1. Before we continue, I would like us to look into the two words that make up organic chemistry. The two words are organic and chemistry. The word organic, as an adjective to the noun chemistry, means something derived from organisms containing carbon. The other word is chemistry. We define chemistry as a branch of pure science that studies matter, which may be elements, compounds, and mixtures, under the compositions, structure, properties, and changes of matter. Knowing the meaning of organic and chemistry, we now define organic chemistry as a branch of chemistry which studies chemical substances derived from organisms which contain carbon, apart from the following carbon compounds: carbides, cyanides, oxides of carbon, and trioxocarbonate 4. If you look at the definition, you will see that all organic matter contains carbon element. So, the center atom is carbon. Then, we have to look into the carbon atom. Recall that an atom is the smallest part of an element that possesses its chemical properties or can take part in a chemical reaction, whether capable of existing alone or not. And for carbon? When we say carbon atom, we are talking about this smallest part of carbon element that can retain the chemical properties of carbon element. Atom of an element carries the chemical characteristics of the element. And the best way to look into an atom chemically is by looking at the electrons of the atom and its arrangement. So, we are to look into the carbon atom electron number and its configurations. Carbon atom has 6 electrons. That is 6 negative subparticles orbiting around its nucleus. And 6 protons. Note that protons are positively charged particles found in the nucleus of an atom of an element. Therefore, the equal positive and negative charge particles makes the atom of carbon a neutral particle. The number of protons in an atom is also called the atomic number, which for carbon is 6. The change in electron arrangement is responsible for chemical changes. The arrangement of electrons around the nucleus of any atom of any element is called electron configuration. In the distribution of electrons into orbitals, the following rules should be observed. The Aufbau principle. This states that electrons enter the lower orbitals first. It means that 1s orbital should be completely filled with electrons before filling 2s. Also, 2s orbitals should be filled completely first before filling 2p orbitals. But if the orbitals are of the same energy, as in 2px, 2py, and 2pz orbitals of subshell, we follow a different rule called Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity says that electrons enter the degenerate orbitals, or, which is, orbitals of the same energy level singly before pairing occurs. It is only the s subshells that have no multiple orbitals. P, d, and f subshells have degenerate orbitals, or, which can also be called, multiple orbitals. Here, their orbitals have the same energy level. For instance, px, py, and pz are 3 different orientations of p subshell. We fill the electron like this: 1 for px, 1 for py, and 1 for pz. Then pair them if there are still more electrons. That is what the rule means. This is because the 2p orbitals have the same energy level. The next is Pauli's exclusion principle. This emphasizes that the electron position in an atom is unique. It shows that, since each orbital can contain 2 electrons maximum and different spin numbers, it will be impossible for 2 electrons in the same atom to have the same all 4 quantum numbers. Using the SPDF notation, the electron configuration of carbon is 1s2, 2s2, 2p2. Bringing in the KLMN electron configuration, we have 2, 4. This electron configuration shows that the atom of carbon has 4 valence electrons and 4 bonding electrons. But it reveals that there are only 2 unpaired electrons in the p subshell. This electron configuration is said to be the ground state electron configuration of carbon. At the excited state of carbon electron configuration, we have 1s2, 2s1, 2p3. This is because one electron was promoted from 2s to 2p subshell. Here, there are 4 valence electrons, 4 bonding electrons, and 4 unpaired electrons, and each of these will be represented in the study of organic chemistry as 4 lines. Nitrogen will be 3 lines, representing the 3 unpaired electrons. Oxygen will be 2 lines, from the 2 unpaired electrons, and hydrogen will be only a line, since it has only 1 unpaired electron. When you see a line, 2 lines or 3 lines connecting 2 atoms, the line represents a bond pair of electrons. That is, 2 electrons from 2 unpaired electrons of 2 atoms forms a single bond. 4 electrons from 4 unpaired electrons of 2 atoms form a double bond. And 6 electrons from 6 unpaired electrons of 2 atoms form a triple bond. So, this shows that the ordinary covalent bonding is mainly of bondings using 2 unpaired electrons from 2 different atoms to form a bond pair of electrons. A carbon atom can form 4 possible bonds for a complete bonding using the 4 unpaired electrons. It can be all single bonds, all double bonds, or a double bond and 2 single bonds, or a triple bond in a single bond. Don't forget this when making a structure of carbon. Carbon must have 4 lines around it in any organic compound. In summary, from the beginning, this lesson introduces organic chemistry by defining organic as carbon-containing substances from organisms, and chemistry as the study of matter and its changes. Organic chemistry focuses on carbon compounds, excluding carbides, cyanides, oxides, and carbonates. The carbon atom, with 6 electrons and protons, is neutral. Its electron configuration, ground and excited states, and bonding patterns explain how it forms single, double, or triple bonds. Yet, the question is, how do carbon atoms form single, double, or triple bonds to themselves or to other atoms as seen in diamond, graphite, and organic compounds? The answer is found in hybridization. We will discuss hybridization in our next lesson video. Be there.